So I'm happy to welcome Alberto for his second part of his talk. He'll talk about partial resolutions of affine symplectic singularities.
All right, so thanks to everyone who made it again. So I wanted to start with just kind of a recap of mostly just terminology and everything down. So I'm gonna try to keep this consistent throughout the talk. So X is going to be always a conical affine symplectic singularity. So symplectic singularity means it's essentially a singular version of a symplectic manifold. It has a symplectic form on the smooth locus, and there's another condition which isn't so important right now. Then X prime is going to be a partial resolution, and it's going to have this symplectic condition that the symplectic form here extends to a symplectic form on the smooth locus here as well, and that turns out to be equivalent to being crepant. And finally, Y is what's called a cubic terminalization, but that's really just a maximal sort of partial resolution. So for the rest of the talk, I'm just going to say partial resolution for these, sort of that adjective is always going to be the same. This is the correct type of partial resolution for what we're thinking about. Y is always going to be a maximal partial resolution, and the maps are also always going to be rho and pi prime and pi. So I'm going to leave this up. So the other thing, last time we talked about a lot, is that to each conical affine symplectic singularity X, we can assign Wx, which is called the Malaney vowel group, and it's a Coxeter group. So if X is the nilpotent cone of a Lie algebra, then it's just its vowel group. And last time I also associated to a partial resolution a parabolic subgroup of Wx, which I'm also going to call the Malaney vowel group of the partial resolution. So if we don't remember exactly what the definitions are, that's okay. But those are sort of the data that are going to come up. So now I want to pick up talking about deformation theory, which is where I left off. So one feature of all these symplectic singularities is that the symplectic form doesn't extend as a symplectic form, but the non-degenerate Poisson structure induced by it does extend to make all these Poisson schemes. So everything is going to have a Poisson structure. And in particular, it turns out that the correct notion of deformation theory for our purposes, the one that's going to work, is going to be deformation theory as a Poisson scheme. So if X is a Poisson scheme, but if this is unfamiliar, also just think that this is basically the same way deformations are always defined. That's just the data we're keeping track of. So this functor of Poisson deformations of X is going to be a map from Artinian rings over C to sets, and it's just going to be defined to send an Artinian ring to the set of schemes over spec A, which are flat and Poisson, plus the data of an isomorphism between the special fiber of this deformation XA and the scheme that we started with. So this is really the way deformations are usually defined, just the Poisson structure is part of the information that we're keeping track of. So one fact which I wanted to briefly mention just about deformation theory that's going to be important is that if F is a deformation functor, and it's pro-represented by a ring R, so that just means essentially it's represented by a ring R, but R might not itself be an Artinian ring, it might be some kind of a colimit of Artinian rings, like a formal ring of polynomials or something. So it's pro-representable by R, and smooth. And smooth means that you can always extend deformations, but it works out to just be a condition on R now. It's going to turn out that R is always just isomorphic to a formal ring of polynomials on the zero, you take the tangent space and then you take the form of neighborhood of zero. So what this means is I take the tangent space of the functor, tangent space is what you get when you plug in the dual numbers. I take the form of neighborhood at zero and I take functions, and that's just going to be the ring. And in particular, this means that R will just be isomorphic to a polynomial ring a formal polynomial array in n variables, or n is the dimension of the tangent space. So the motto is essentially, if you have a deformation functor and it's both smooth and pro-representable, then the tangent space just knows everything about the functor. It really determines it, has all the information, and in particular, there exists a universal formal deformation over the formal neighborhood of 0 in the tangent space. So we can then make this precise by actually just assembling everything into a universal formal deformation over the tangent space of 0. So Namikawa studied the deformation theory of x and y sort of very extensively, and this was studied over the course of many years and many papers. So I'm going to just sort of quickly assemble some of the greatest hits of all these results. So first of all, Poisson deformations of x and Poisson deformations of y are both smooth and pro-representable. So they have these nice properties that we wanted. Secondly, the tangent space of Poisson deformations of y is actually isomorphic to the second cohomology group of the regular locus of y. This might seem random, but if you recall, this is actually the same vector space that came up last time, which also sort of controlled the birational geometry of this whole situation. So, it's a vector space that tends to have be a recurring theme. And the next thing is that there exists a push-forward functor from Poisson deformations of y to Poisson deformations of x. So this is, in this case, it turns out not to be super hard to prove, but this is like a very unique thing in general. So you don't expect that deformations can push forward. That's not a standard functoriality. So this is some of the theory, some of the setup, and then it turns out that also with some work of Losev, sorry, K2, there exists a diagram of universal deformations, and I'm just going to write it over here and try to keep it up. So the diagram looks like this. So y maps to x, and then y includes into its universal deformation curly y and x into its universal deformation curly x. As stated over here, the base of this universal deformation, I'm going to write as by from now on, is going to be the second cohomology group of the regular locus of y. But then it's going to turn out that this base is the base of y mod this Namikawa value. So another thing he constructs is an action of the Namikawa value group on this tangent space, which I'm going to talk about more in a second. But the diagram looks like this. So this is a direct generalization of the Grothendieck-Springer resolution for the nilpotent cone, and there's a couple important observations. So the key thing is that this Namikawa value group really controls the difference between the deformation theory of y and the deformation theory of x. The other observation is that based on sort of just these formal results, we would get a universal formal deformation over the formal neighborhood of 0 in these bases, but we can actually use the C-star action to expand it to a deformation which just lives over the entire tangent spaces, over these affine spaces. So these are bona fide living over these entire vector spaces. Okay, so as I said, this was proven over the course of a long time and a lot of work, but I want to give sort of one sort of nugget of an idea in the proof, which is really just where this Namikawa value group makes an appearance, kind of mysteriously. So for that, we need to talk briefly about Affine singularities. So let's say we have a Affine singularity S, and we have a unique, so every Affine singularity has a unique resolution, a unique symplectic resolution S tilde. And we talked about last time how the exceptional fiber of this resolution is basically a union of P1s in the shape of the Dindon diagram corresponding to that Affine singularity. So we can obtain directly a deformation, a universal deformation of the Affine singularity and its resolution by looking inside the Grothendieck-Springer resolution. So you can take the corresponding Lie algebra, then take a transverse slice the subregular orbit of the nilpotent cone, and that's going to get you a deformation of S living inside the Grothendieck-Springer resolution, and similarly of S tilde. So these two embed inside universal deformations, which live inside the Grothendieck-Springer resolution. And now, because it's inside the Grothendieck-Springer resolution, the bases of these deformations are going to be H and H mod W. So we see here the first appearance of a Weil group. So then now the question is, how do we reduce down to Kleinian singularities? So if we have Poisson deformations of Y mapping down to Poisson deformations of X, one thing I described last time was if you take any of the codimension 2 symplectic leaves of X and you take a transverse slice, you get a Kleinian singularity. So just restricting to each of those, what we get is we get a functor to a direct sum over all the codimension 2 symplectic leaves of the Poisson deformations of that transverse slice. And then similarly, if you restrict the preimage, you'll get a deformation of the resolution of that Kleinian singularity. So we just get a diagram of functors that looks like this by sort of restricting to the neighborhood of a point in every codimension 2 symplectic leaf. But these functors are all super nice. They're all smooth and pro-representable and have all the good properties that we want. So this map of functors is really just equivalent to a map of the bases, their universal deformations. So that map looks like the base of Y goes to the base of X, goes to the Lie algebra corresponding to each codimension 2 symplectic leaf, and then over here, the Lie algebra mod the Weil group. And the reason why I have these hats is because these are the Lie algebra and the Weil group corresponding to each of the transverse slices, each of these Kleinian singularities. But what we learned last time is that there's an action of the first fundamental group of each of these codimension 2 symplectic leaves on the Dinkin diagram corresponding to that Kleinian singularity by graph polymorphism. So what we get is a folded Dinkin diagram. So what I really want to think of is not the Dinkin diagram corresponding to the Kleinian singularity, but the Dinkin diagram corresponding to the Kleinian singularity mod the monodromy action of the fundamental group. And because these deformations have to essentially be locally trivial along the codimension 2 symplectic leaf, the image of these restriction maps is just going to be the invariance under the monodromy action of the fundamental group. So it's just going to work out that these maps surject onto H and H mod W for the folded Dinkin diagrams. So we get a diagram like this, but now it's actually surjective. And then it turns out that this diagram is Cartesian, and then this gets us that the base of Y is isomorphic to the base of X. Sorry, the base of X is isomorphic to the base of Y, mod the direct sum of all these Weil groups. And last time the direct sum of all these Weil groups is exactly how we defined this non-color Weil group of X. So essentially we look at the Kleinian singularities, we get the appearance of the corresponding Weil groups, and then by sort of an argument sort of restricting to each of the Kleinian singularities transverse to each of the codimension 2 symplectic leaves, we find that the deformation theory of those Kleinian singularities completely controls the difference between the deformation theory of X and Y. Okay, so any questions about all of that? Okay, so if there's no questions, then so now what we want to do is we want to integrate partial resolutions into the picture. So so this is all work with Namikawa, but now what we want is we want to integrate partial resolutions into this picture. So let's do that. So So theorem. So firstly, the Poisson deformations of all the partial resolutions also have all the nice features that we want. So PD of x prime is also smooth and pro-representable. Secondly, we have the deformations, the map on deformations from PDY to PDX factors through deformations of x prime. So we have 1/3 PDY, x prime, x. And then finally, now we have the tools to hope at least for a diagram of universal deformations, that we do in fact have diagram of universal deformations. So what I want to do here is I just want to add it to the existing picture. So what we have here is just what was already known, sort of by work mostly of Namikawa, but then I'm just going to add in a different color, sort of the new pieces. So here we have the partial resolution, and then it turns out that this also includes universal deformation, and that this deformation lives over the space of y, but now not the Namikawa power group of the partial resolution. And this all commutes with the diagram that existed before then, and all of that. So that's the last part of the theorem. So why is this? Well, maybe let me start with why is this exciting, and then I'll say why it's true. So why is it exciting? I want to give 2 reasons. So reason 1 is that this Namikawa value group initially emerged really from this diagram. So it's important because it measures the difference between the deformations of y and the deformations of x, even though you can define it just sort of by looking at Affine singularities and such. This is really where it appeared. And now the Namikawa value group with the partial resolution appears in exactly the same place. So that really justifies the name. It wasn't just like some kind of arbitrary thing that you could define. It really plays the exact same role. It measures the difference between the deformation theory of y and the deformation theory of x prime. The second reason why this is important is because this is exactly the diagram that we need to do Springer theory for partial resolutions of symplectic singularities. So last time I started off with drawing the Grothendieck-Springer resolution, including a column in the middle, which had a partial resolution and its universal deformation. And this diagram is now the strict generalization of that one, and it's exactly what we need to do Springer theory for partial resolutions, which is the next section. So before I get there, maybe let me just say one word about how this Namikawa value group of the partial resolution makes an appearance. So essentially, we once again look at Affine singularities. But now we don't just look at a Affine singularity and its resolution, we look at a Affine singularity and the partial resolution. But now, as we said before, the exceptional fiber of this resolution is just a union of P1s in the shape of a Dinkin diagram. So what we can do now is we can take the subset of that Dinkin diagram corresponding to curves contracted by this map. So we'll get just a subset of the Dinkin diagram. But now it turns out that the singular locus of S prime has a very concrete description. So the singular locus of S prime is a union of points, and those points are in bijection with the connected components of this subset of the Dinkin diagram. So it is a union of points in bijection with the irreducible components of D prime. And if we have an irreducible component di prime j, then the corresponding point has di prime j type prime singularity. Okay, so essentially, just to recap, so the singular locus here will have one point for every sort of connected component of the curves that are contracted, and then the singularity there will just be the singularity corresponding to that tangent diagram. So it's all highly explicit. So now, if we do a very similar trick to here, just restricting to a point around each of those singular points, what we'll get is that each point corresponds a Weil group of the tangent diagram corresponding to that irreducible component. And if we take their direct sum, we'll just get the parabolic subgroup of the Weil group, which corresponds to the one generated by all the single generators, which are contracted. So we'll get precisely the theorem for Kleinian singularities. So just analyzing each of those points separately, keeping track of the Weil group that we get, gives us the appearance of the correct group for Kleinian singularities. And then now we do a similar trick, we just keep track of partial resolution throughout. So if we now have a partial resolution, so instead of just PDY going to PDX, we have PDY going to PDX prime, going to PDX. Then as before, if we take a transverse slice to each codimension 2 symplectic leaf, we get a Kleinian singularity, and those Kleinian singularities all get resolved in Y. But what we also have is that they get partially resolved in X prime. So we get a diagram like this with an extra column. This diagram is similarly determined by its bases. The map here is similarly given by taking a variance under the appropriate monogamy action of the fundamental groups of each of the codimension 2 symplectic leaves. And then in the end, what we have is we just have a diagram that looks like this. So the base of Y goes to the base of X prime, goes to the base of X. Here we have direct sum over all the codimension 2 symplectic leaves of the corresponding Lie algebras. And then here we have a direct sum over all the codimension 2 symplectic leaves of the Lie algebras mod the Weil group of the partial resolution, which we get in X prime. And the last observation to make is that these Weil groups really keep track of exactly which curve classes are contracted, and that's exactly how we defined the non-curve Weil group of the partial resolution last time. It's sort of determined by which curve classes are contracted by the map from Y to X prime. So combining everything, we get that Bx prime is indeed By mod this non-curve Weil group of the partial resolution. So, just to recap again, we do an argument where we see what happened for Kleinian singularities, we study its singular locus, and then we do kind of a reduction of Kleinian singularities trick. So that's the idea. So any questions about all that?
Will each one of these squares be Cartesian?
Yeah, so that's sort of the last step, yeah. So similarly to before, each of these squares will be Cartesian, and since here this is just a quotient by the direct sum of each of these Weil groups, and this is yeah, thanks. It's an important observation. Anything else? Okay, so then we're moving on to Springer theory. Okay, so if everything that was said so far was confusing / relied on things we don't remember from last week, that's okay starting now. So what we need is really this diagram over here. So this diagram is the diagram that we need to do Springer theory, and I'm gonna leave it up. Okay, so in Springer theory, one category that we tend to love and want to study all the time is perverse G-equivariant sheaves on the nilpotent cone. This is the category that comes up a lot. So the first observation I just want to make is that if G is of adjoint type, this category turned out to be isomorphic to the category of perverse sheaves, which are constructible with respect to the nilpotent orbits, which, as I mentioned last time, turned out to be the same as the symplectic leaves. So I'm denoting that category like this, and I'll just write the definition down under. So this category of symplectic of X is the category of perverse sheaves on X, which are smooth with respect to stratification by symplectic leaves. And this category is a category which we study a lot for the nilpotent cone, so this is a very natural generalization. So the other thing I wanted to recall was that also for the nilpotent cone, we have the Springer resolution, but we also have partial resolutions, which are given by conjugacy classes of parabolic subalgebras. So if you just replace Borel's with conjugacy classes of parabolic subalgebras, what you get is naturally a partial resolution. And naming these maps the same as I've been naming them throughout, it's a theorem which is very old by Borho and MacPherson from 1984. So before symplectic singularities were even invented. That you can compute the cohomology of the partial resolution just by taking the cohomology of the full resolution and then taking the invariance under the Val group of the levy. So, you know, as I mentioned last time, I was very intrigued by finding an analog of this theorem for a general symplectic singularity, and what you need is really a diagram like this one. So for the nilpotent cone, gets you the Grothendieck-Springer resolution, and theorems like this are generally proven by saying, okay, if we have something for the nilpotent cone, and the Springer resolution may be a partial resolution, think of whatever is going there as some sort of a degeneration of whatever is happening on the whole Grothendieck-Springer resolution. So I wanted to make that type of argument. And before this theorem, we didn't have the right generalization of the Grothendieck-Springer resolution. Okay, so now we do. So let's go ahead and do that. So another quick thing I wanted to briefly mention is that from now on, I'm going to require that y is a symplectic resolution of X. So y to X symplectic resolution. This is mostly a technical point. I just don't want to say things which are not true. But the reason why we need this is because there's a theorem by Claydon in 2006, which says that if this is true, then the map from y to X is semi-small, which is also exactly sort of the type of condition that we need to do Springer theoretic arguments right now. So it's actually not known if y is not a symplectic resolution, if it's just a Q-terminalization, if the map is stratified semi-small, or if there's any type of good smallness conditions that can be made, and I would love to know. Maybe that would be a very interesting fact. Okay, so this study of this category was really begun recently in a paper by McGerty and Nevins from 2019. So I'm going to quickly just write a few of the facts that they found. So first, we're going to define the Springer sheaf to be the push forward of the constant sheaf on Y. So the Springer sheaf goes over here. And then the Harasander sheaf is going to be its analog on the universal deformation. So it's going to be the push forward of the constant sheaf on the universal deformation. Let me quickly name these maps. So these were rho and pi prime. And then so I'm just going to call these rho tilde and pi prime tilde. And then, so pi is the composition of these two, and r tilde is the composition of these two. Okay, so we can make these definitions. So the first thing to say is that the Springer sheaf is indeed an element of this category. So this is definitely something that we need. We want this category to be the right thing to study in Springer theory. The second thing is that the endomorphisms of the Harasander sheaf are isomorphic to the group algebra of the non-Kavah groups. See here the non-Kavah group appearing. We also have that if we pull back the Harasander sheaf, then we get back the Springer sheaf. So you can hear this map over here as I. So I want to make a couple observations about this. So the first thing is that fact 1 comes from a nearby cycle construction on the entire universal deformation. So it really does actually use, so when Nevins and McGerty wrote this, the middle column wasn't here, it was just top and bottom, but this fact really uses the universal deformation. So it comes from nearby cycles on the universal deformation. The other reason why this is important is because it actually turns out that we can define the Springer sheaf not just as the push forward of the constant sheaf on Y, but also just using a nearby cycles construction on the bottom row. So the Springer sheaf doesn't depend on the choice of a symplectic resolution. So for the Springer theory, this isn't super exciting because there's a unique, so the Springer resolution is the unique symplectic resolution of the nilpotent cone. But for a general symplectic singularity, it's sort of a very interesting, maybe surprising fact that the Springer sheaf doesn't depend on a choice of symplectic resolution. The other thing which I wanted to mention is that fact 3 gives us a map from endomorphisms of the Harish-Chandra sheaf to endomorphisms of the Springer sheaf. So in particular, it gives us a map from the group algebra of the Nilpotent group to endomorphisms of the Springer sheaf. So we might recall that in Springer theory, there's this isomorphism between endomorphisms of the Springer sheaf and the group algebra of the Weil group, which is also the same as the top word on cohomology, the Steinberg variety. So it has this convolution structure coming from a couple different places. So for a general symplectic singularity, you just get a map. So endomorphism of the Harish-Chandra sheaf for the group algebra of the Weil group, and endomorphism of the Springer sheaf might not be, but we still get this map. Okay, so a couple of final observations I wanted to make about this diagram, because this is the type of thing that we tend to use, is that just like for in the Grothendieck-Springer resolution, this map over here is generically a cover by this group over here, and the composition is generically a W cover. So these two right squares they're not Cartesian, but they're generically Cartesian. So the reason I'm bringing this up is because for the Grothendieck-Springer resolution, usually when you start with something here, you treat it as a degeneration of something there. Then you use the fact that over here, these maps are almost just covers by the non-Weil group. Okay. Any questions about what's been said? All right. So it turns out that sort of all the techniques that Nevins and McGerty use can kind of extend to the partial resolution case quite automatically. So they really only use things sort of about the symplectic and Poisson structure, and just geometrically about perverse sheaves and such and such. So I'm just going to leave it as a lemma that the theorem over there, the theorem over here, applies, replacing y to x with just a map from y to partial resolution. So then in particular, we'll also replace the Springer and Harish-Chandra sheaves with a partial Springer sheaf that lives over here and a partial Harish-Chandra sheaf that lives over here. So this might not seem that exciting as of now, but what does make it more exciting is that now we can study Springer theory sort of compatibly for different partial resolutions. So for the entire co-set of partial resolutions at once. So I'm going to kind of illustrate that right now. So let's say I started with the constant sheaf on the universal deformation of y. So over here, so I can pull it back to get to the constant sheaf on y. But I can also push it down, and then what I'll get here is defined to be the partial Harish-Chandra sheaf. And now if I keep pushing that down, then what I'll get is just to push for the constant sheaf all the way down to curly x. So I'll get the Harish-Chandra sheaf over here. And then similarly here, if I push down the constant sheaf on y, I'll get the partial Springer sheaf. This diagram will all commute by some combination of this third theorem and proper base change. And similarly down here, I'll get just the usual Springer sheaf So we'll get a diagram like this, and just to be super clear, this is all living on this left rectangle. So all these different Springer and Harshon sheaves for different partial resolutions interact. And if I wanted to, I could consider like a bigger sort of sequence of partial resolutions. I'm just considering just 3 sort of for simplicity. So what are a couple of things that I can do with this? So the first sort of exciting thing I can do with this is I can take endomorphisms of the bottom square. Okay, so what am I going to get? So I'll get endomorphisms of the Springer sheaf, mapping of the partial Springer sheaf, and endomorphisms of the Springer sheaf, and then here I'll get endomorphisms of the partial Harshon sheaf, but that's going to be the group algebra of the Namakalov algebra of partial resolution, and here I'll get endomorphisms of the Harshon sheaf, and that's going to be the group algebra of the full Namakalov group. This will be the natural inclusion, and I'll get a diagram like this. So a couple observations to make about this diagram. So for the nilpotent cone, some people might assume the theorem that this endomorphism of the Springer sheaf is isomorphic to the top Borho homology of the Steinberg variety. So the Steinberg variety is y times over x with y. And this sort of only uses kind of convolution sheaf tricks. So this applies verbatim, and it's in Nevins and McGerty's paper. It applies verbatim for any symplectic singularity. And then this has a natural convolution structure, which is isomorphic to the endomorphism structure here. We can also do the same thing over here, and this will be isomorphic to top Borho homology of z prime, where we define z prime to be y times over x prime with y. So what we've actually obtained here using these endomorphisms is a finer invariant that we can identify with symplectic singularities and their partial resolution. So the most natural invariant that people identify as a symplectic singularity is this Namakalov algebra. And now to a partial resolution we can apply the Namakalov algebra with a partial resolution. But that turns out to be quite a coarse invariant. So a lot of interesting, exciting symplectic singularities still have trivial Namakalov algebra. If it has trivial Namakalov algebra, then every subgroup will be trivial as well. These algebras turn out to know a lot more about what's going on. So these push forward, these Springer sheaves and partial Springer sheaves, they know a lot about sort of the cohomologies of the fibers and things like that. So this is a more fine invariant, but the invariant comes with a natural action of the Namakalov algebra. So it doesn't exactly replace it, it sort of enhances it. And it also turns out that these maps all turn out to be inclusions. So the same way that for every partial resolution, we get a subgroup of the Namakalov algebra. Now for every partial resolution, taking endomorphisms of the partial Springer sheaf gives us a natural sub of this algebra, which they already discussed in McGerty's paper. Okay, so that's sort of exciting thing 1. Exciting thing 2 is that we have a natural action of the Namakalov algebra on this bottom row over here, as discussed, and of the Namakalov algebra with a partial resolution on this middle row. So the Namakalov algebra of the partial resolution acts on the whole bottom square. So we can take wx prime invariance of the bottom square. So that's going to get us just having the invariants everywhere, and sort of these maps are all wx prime equivariant, so the invariants will naturally map to the invariants. So we got a map like this. But now, this here was generically a wx prime cover. So this Harshon sheaf is sort of an IC extension of the regular representation of this group. And when we take the invariants, we get an IC extension of the regular locus of this universal deformation. So So this object here becomes something maybe more familiar or easier to digest. You don't want to write the constant sheaf. And this actually turns out to be the information that we need to prove the theorem I alluded to at the beginning. So we need a condition. So if the universal deformation of x, curly x prime, is rationally smooth, then we have the theorem that we had desired, which takes the form here that the cohomology of the fibers of the partial resolution are given by taking the cohomology of the fibers of the full resolution and now taking invariance under the action of the non-Cow-Val group of the partial resolution. And the proof actually turns out to be quite straightforward once we have all the tools. So if curly x prime is rationally smooth, that means that this IC extension is just going to be the constant sheaf. That's exactly and precisely the reason why we need that condition. So that tells us that the sheaf is just going to be the constant sheaf on the universal deformation of x prime, but then the constant sheaf is going to pull back to the constant sheaf. So now this sheaf, taking this partial Springer sheaf and taking the invariance, is also going to be a constant sheaf. And then now, pushing forward here, so that tells us then that taking the Springer sheaf and taking the invariance is by definition just going to be the push forward of the constant sheaf. And now we just need to remember what the Springer sheaf was. So this Springer sheaf over here is already the push forward of the constant sheaf all the way on y. And now we get that if we take the invariance under this Cow-Val group of the partial resolution, we get the push forward of the constant sheaf on x prime. And then the fibers of these two sheaves are exactly these cohomology groups. So taking fibers, we're done. So this is sort of what I was hoping to get at the beginning. So we do need this condition. This condition is quite essential though, because there are some symplectic singularities where the non-Cow-Val group is trivial or just very small. It just doesn't know enough about the symplectic singularity, and where these still can turn out to be radically different, but this group is trivial, for example. So turns out some condition is definitely necessary. That became evident quite early, but this condition turns out to be enough. And in the nilpotent cone case, these are all going to be these G tilde P's, which are completely smooth. So this is sort of a strict generalization.
Yeah.
So that's all I have to say about Springer theory. Any questions about what's been said? All right.
Sorry, I mean,
yeah.
so do like the Springer fiber, are there analogs of Springer fibers and everything in this picture?
Yeah, exactly. So the Springer fibers are the fibers of, so the Springer fibers would be the fibers of this map, and
Right.
partial ones would be the fibers of this map. And naturally, because of that theorem, so this will have a natural convolution action on the cohomology of the fibers.
Right.
And as I mentioned before, we have, well, it's actually right here. So we have this map. So all of the Springer fibers have a natural action of the non-Cow-Val group, and now all the partial Springer fibers have a natural action of the partial non-Cow-Val group in a way that's consistent.
So do you get like so you get an action on the top dimensional cohomology, and do you get the irreducible representations that way for the non-Cow?
So that actually doesn't work quite as well. So you get representations for sure.
Yeah, okay.
But the representations don't necessarily turn out to be irreducible.
Okay.
So there's a theorem that I didn't want to include more stuff on the board, but that theorem that the irreducible representations are included into the category of perverse sheaves is replaced by an adjunction between the category of representations of the non-Cow-Val group and the perverse, the category I define perverse sheaves with respect to symplectic leaves. So you do get an adjunction. I mean, the other thing to be said is just that this group is like often trivial. So sometimes you would get very boring representations, but there is a specific example in Nevins and McGerty's paper of a non-irreducible group.
Okay. Thanks.
Any other questions? All right, so then, okay, so this is the end of sort of the content of my thesis. I wanted to very quickly go over one project which I'm working on now, which sort of expands on this. So, as I sort of said at the beginning, I kind of think of this as developing a theory of parabolic induction and restriction for symplectic singularities, because for the nilpotent cone, partial resolutions come from conjugacy classes of parabolic subalgebras. So I want to give one example of sort of how that works in theory. So recall, let's let curly p, that looks too much like rho, let's let curly p be a conjugacy class of parabolics. So then we get a partial resolution until the p goes to n. So in particular this can be written, so well, let me say exactly what this is. So this is going to be given just like the Springer resolution by pairs, nilpotent elements and Borels in this conjugacy class that we fixed, such that x is in P. But messing around with it, we see that this is isomorphic to G crossover P, which so P is some parabolic subgroup which has that as this Lie algebra, but it has this description. So it turns out that there's a bijection between nilpotent.
The P is supposed to be the unipotent, right?
We'll get it. So until the P is, the way I defined it is just like that. So there's a bijection between nilpotent orbits of the levy and symplectic leaves of until the P, and this bijection is given by sending a nilpotent orbit L to G crossover P with the nil radical plus the orbit. So what you said is what you get if you take the trivial symplectic leaf, or the, not trivial, the zero symplectic leaf of the levy, then you get T star G mod P, which is indeed G crossover P with N for U. So this T star G mod P is what we often study when we think about Springer theory for parabolics, but it actually has something to do with partial resolution, something very specific. It's the unique closed symplectic leaf of the partial resolution. So in particular, now just sort of working through our diagram, so we started with the nilpotent cone. We took our partial resolution. Now we took a closed symplectic leaf, turns out to be the unique closed symplectic leaf in this case, and this has a finite to one map down to the closure of a Richardson orbit, the nilpotent cone. So this map, in general, is finite, and the index is what people call the Hesselink number. The other sort of tiny technical thing I want to mention is that this lifts to a finite map from T star G mod P, not just to the closure of the nilpotent orbit, but to the normalization of that space, just because that's what you need to get a symplectic singularity. So in general, if you just take the closure of a symplectic leaf, you don't get a symplectic singularity, but if you take its normalization, you do. So there's this very deep theorem by Fu, which is very early in the symplectic singularities phase, which is that every symplectic resolution of a nilpotent orbit closures of this form. So this is not just like some random way to get symplectic resolutions, it gets all of them. And furthermore, so this kind of tells us that this gets us all the symplectic resolutions. The other thing that's been done is people have studied a lot the symplectic data of these resolutions, so the base of the universal deformation and the Namakawa vowel groups, and found that those kind of come from the symplectic data of the entire nilpotent cone by a kind of parabolic restriction as well. So in particular, Namakawa showed that the universal deformation of P star G mod P actually lives inside the universal deformation of the partial resolution, which is G tilde P. Furthermore, the base, so B P star G mod P, is just given by taking the base of the universal deformation for the whole nilpotent cone, and then taking the variance under the Val group of the levy, which agrees with the Val group of the partial resolution. And then finally, the Nanakawa Val group of, I really should write a normalization there, but the Nanakawa Val group of this symplectic singularity is just given by taking the normalization of the Nanakawa Val group of the levy mod the Val group of the levy. So all this data sort of comes from, it kind of all sits inside the data of the original symplectic resolution and the partial resolution.
Sorry, I'm a little confused. So
Okay.
suppose you take this picture for GLN.
Sure.
Right. So you have a Richardson orbit down there.
Yeah.
That's going to be normal for GLN, right? And this map over here is actually resolution singularities in that
Yeah.
case, right? So this finiteness comes from like the connectedness of the, yeah, so you have to look at the centralizer and see if it's connected. And if
Yeah,
it,
so the Hesselink number has an explicit computation.
Right.
It's in this paper, and it's,
okay, so if the,
but in type A it's always one.
it's always one,
Yeah.
okay, all right.
Type A it's always one.
Okay, so I get a better feel for this.
Yeah, it's also usually one.
Okay, all right.
But yeah, and this theorem only applies like, when it's one, because otherwise it's not a symplectic resolution.
Okay, thanks.
Okay, so if we kind of follow and try to do the same thing for a general symplectic singularity, it turns out you actually can. So if you just have the general case, so what you do next, you take a minimal symplectic leaf. I'm going to call this y0 inside x prime, and because essentially because these are all Poisson maps, this is actually going to map to the closure of a symplectic leaf in x. And it turns out that this map, if y is a symplectic resolution, this map is also going to be finite. And this follows from semi-smallness, it turns out. So what we have here right off the bat is a notion of being a Richardson stratum. So we have a notion of being a Richardson stratum and of a Hesselink number. So both of those things apply, and what I want to say is definition. If a symplectic resolution is obtained as above, I want to say it's obtained by generalized parabolic restriction. You just want to call this procedure generalized parabolic restriction. So you take a partial resolution, you take a minimal symplectic leaf, and then you get a finite map, and if it's birational, you call this generalized parabolic restriction. So now there's a couple natural questions you can ask, which I was going to write down. But so the first question is, does Fu's theorem hold? Which is, that every symplectic resolution is of this form. The second question is a bit more abstract, but it's essentially, can you get something like a Q terminalization of every single symplectic leaf closure by this kind of procedure? Because I only presented sort of the symplectic resolution perspective, but Losev actually kind of generalized this and studied the symplectic data of all the nilpotent orbits, looking at Q terminalizations instead of symplectic resolutions. So the answer is that Fu's theorem, and also the other theorems I said about this applying to all symplectic leaf closures, doesn't hold. And this is because there's symplectic resolutions like Sn of C2, which just don't have any intermediate partial resolutions, for example. But actually, the other question though is, if you do have a symplectic resolution obtained by generalized parabolic restriction, can we say something like this? So can we somehow derive its symplectic data from the data that we started with? And for this question, I believe that the answer is yes. So I'm going to put this sort of in conjecture form, though sure for various parts I feel like I have some sketches of arguments here and there, but Suppose y0 x0 is obtained via, just gonna write generalized parabolic restriction. So obtained the way we did it before. Then first of all, every symplectic resolution of x0 is. Second of all, the universal deformation of y0 sits inside the universal deformation of x prime, and then the base of the universal deformation is a subset of the base of y, and then you take the invariance under the Nilpotent group of partial resolution, and the Nilpotent group of x0 lives inside this normalizer. And then it turns out that in a lot of cases you don't get equality, but I do think under some semi-strong conditions. So if y0 is the unique closed symplectic leaf, and y0 fully contains sort of the central fiber, then I'll just write equality above. So yeah, that's it.
Questions for the speaker?
Yeah.
I don't really have a question. It hasn't become a question, but this group, like in the setting of Springer theory, this normalizer of the Weil group for the levy mod the Weil group for the levy is called the relative Weil group.
Yeah.
And it turns out that it shows up when you try to do generalized Springer theory, where you replace the constant sheaf with some other local systems that show up. And it's always been kind of a mystery to me how this group shows up, and I guess you haven't talked about trying to do any of your stuff without the constant sheaf, doing some other kind of system.
Yeah. So
Like I said, it's not
yeah.
really a question,
No, I mean,
but do you have
I'll give you my
about,
thoughts. Yeah. So if you take the constant sheaf on y, you push it all the way forward, it'll have an action of that Nilpotent group. If you take some kind of an IC extension here and you push it forward, it should have an action of this group. And essentially this map is stratified semi-small whenever this is symplectic resolution, so like that's a reasonable thing to do. So I mean, so what I would love to do, but this is like nowhere near being done, is like study this category of reverse sheaves here and see like which things come from which partial resolution. So the things which come from a partial resolution should have a natural action of this group with a corresponding partial resolution. So for example, if something comes from y, if we push forward the constant sheaf, then it has a natural action of the whole group.